Okay, good morning, everyone. So today we will move to the new chapter. So this chapter will mainly talk about the mathematics of value and reliability. Especially, we will focus on the mathematical tools that we need to further analyze reliability, especially related to some of the statistical issues. So first is introduction. So this chapter is focused on the mathematical methods that employ in analyze product quality and value data here. So the reliability mathematics and analysis. The purpose that we need to have this reliability mathematics and analysis in the end is we want to in prediction the fate of the product. The fate of product, that means this is kind of like a lifetime. For example, if we consider we stress a device at a certain voltage, for example, Vg equal to 5 volt. And then with a certain proper analysis, finally we can understand the degradation rate for this specific case. For this case, can be, for example, our threshold voltage shift, that's a delta VTH, is equal to 0.02 voltage per hour. So if we do the reliability stress, and in the end we found out that the degradation rate is equal to 0.02 volt per hour. And our target criteria for the value if we want to we set the criteria that the device, once the threshold voltage is reached to this condition, is considered as a complete value. So the criteria to make sure that the device is in the range of the acceptable threshold voltage. So for example, which is our delta VTH is smaller than 1 volt. So based on this spec, so in anyhow our device cannot have the threshold voltage larger than 1 volt. But however, with this stress condition, we always have this degradation rate, which will be the 0.02 volt per hour. So by consider this simple case, we can start to estimate our lifetime. So lifetime, that will be the product, this product can survive less than 50 hours. So that's this number, lifetime, is exactly the fate of the product. So that's a general goal. That's why as being a part of the reliability evaluation, we're not only focus on understand the degradation, in the end, we also has to come up with this degradation rate. In the end, that can give us a lifetime estimation. So then, we consider this simple case, we can know that our product can survive maximum up to the 50 hours. So in order to predict the reliability of failed product, we need to have the extensive time-dependent destructive testing. So the destructive means this is testing. It's a kind of, we will try to test until this device are completely broken. The device will reach to the condition that completely failure. So that's kind of considered as a destructive. And also, on the other hand, it's important because we need to analyze the failure rate. So for sure, when we do the testing, we always have to take into account the time-dependent characteristic. Otherwise, we won't know about the time factor inside. So it's always, when we do this lifetime testing, first we need to spend some time to try to understand the certain parameter, the correlation between the parameter and then the time. And also, we need to test until fail. Because once we test until fail, we can start to know what would be the limitation for our product or our device. What would be the time limitation for our product or our device. So, more extensive time-dependent destructive testing will be required to allow values of failure rates to be determined. So, these are extracted from this is from the other. These are extracted from the other mathematical functions. For example, exponential. The exponential one is the most simple one function we very often use. And for sure, there's some of the function probably you never heard before, but you will have to use this during the reliability analysis. For example, the log normal. And the last one, which is a Weibull distribution. So these three are the most important distributions that we have to learn in the end to use to fit the failure data. So the goals that we have to learn this mathematics, because in the end we want to come out with a lifetime model. So with a lifetime model, we can start to fit the failure data, and then we can start to extrapolate to the condition that we are interested in. But also this condition will be in the range, inside the space of the device reliability. So that's a general goal. And also, because now we need to estimate the lifetime. So another thing is that when we try to do this lifetime estimation, first we need to have this degradation rate. But how do we have have this degradation rate, so we must do the certain time dependent, and also is sometimes related to destructive, because that means every time we need to burn this device, we need to to make it, we need to test this device until the device will reach to the completely failure. Okay, so since the goal, one of the important parts is related to distribution function, now we will start to step by step to let you guys know that why we need this distribution function. And first of all, we use a very simple case to describe that how the distribution function can help us. The first one is a normal distribution function. A useful skill for engineer concerned with product reliability is to be able to convert a large amount of value data into a form that be able for analysis. So because right now if we talk reliability, we're not actually only test one device, we're not only test two devices, because you want to shift your product to your customer. Your customer probably will order huge amount of the product or device from your company. So therefore you need to test a large amount of value data. You probably need to test more than 1,000 or even more than 10,000 of the value data. And sometimes if we just look at this value data, it's kind of like the math. So it's not easy to analyze. So that's why we need to convert to a form that's be able for analysis. So here is an example how to analyze the fuse reliability. So this is a fuse. So you can see the typical way we analyze the fuse is for example, this is a fuse test current. We test the fuse until the completely broken, and then so this is a current. The first current we test until the completely value is a 9.6, and the second one is a 10.22, and then the third one is a 9.46, and in the end the last one is 9.89. So we consider this table. What you have a feeling is that the value current is roughly around 10 amp, but sometimes it's a positive minus with a certain small range. That's only the information we can get if we try to collect the data in this way. So the value current measure for such, this is a population for 100 fuses. So if you try to measure for 100 fuses and want to understand what would be the value curve for these fuses, so then in the end we will get the result like this one. So it is clear that although the value cluster at about 10 amp, but the thing is that there's always a spread that need to further have the statistical analysis. So now you probably can start to give a little bit sense that why we need to have the statistical analysis, because if we just purely collect the data in the table showing here, we cannot do anything. It's just a bunch of the large amount of data sometimes looks like messy here, but this is another form. We cannot do the further analysis. So we definitely need to convert the data showing in this way to the another way that we are able for analysis. So actually the concept is pretty easy. This is a form, the table we already have in the previous slide. But now it is convenient to first create what we call the value frequency distribution. Value frequency distribution. So now you can see we try to define the value current in a certain range, and then we count how many fuses will broken in this range. So for example, if we consider the first current range is 8.7 to 8.9, and then we can start to count inside this table. We found out that there are two fuses will be fail in this range, and therefore we can start to also estimate the cumulative distribution. So since we only have the two fails, but the total what we have, this is if we're starting from these two small to high, so the first cumulative is a 2, but now next range is 8.9 to 9.1. So we found out that there's no fuse value in this current range. So therefore your cumulative number still will be the same, because the cumulative number is a summation of all the fuses below this current range. So that means this value is equal to this plus this will be equal to this one. This plus this will be equal to this one. So that's a cumulative number. So now, if we further start to do this exercise with each state, so now if we look at for the range between the 9.1 and 9.3, so we got the 7 broken. So now you have the total, the number broken below this range, which become 9 here. So because also we test total 100 fuses, so now we can calculate the percentage. The percentage here is just will be equal to 2%. So we have the 2% of our fuses will be valued if the testing current is below 8.9 amp, and also 2% if the testing current is below 9.1, and now it will become 9% if the testing current is below 9.3. So with this exercise so on, in the end, of course, this value will reach to the 100%. So that means with the current, testing current below 10.9 amp, every fuse is broken. So I think this exercise is pretty straightforward. You just try to convert the weight from the spread data to the weight. At least this is something that gives us a certain information. For example, if we are interested in that what would be the current that can lead to 50% of the fuses broken. So that would be roughly around here, 9.9 amp. So that means if we test 9.9 amp in these 100 fuses, that would be roughly around 50% of the fuses will be broken. For this purpose, the range represented by the minimum and maximum current value in the arbitrary group into a number of cells. For example, this is 11 in this example, and number of fuses destroyed in each current interval is noted. So in anyhow, the text try to explain is just as similar to what I explained. So we divide with a lot of the small group. That's what we call the frequency distribution. We count for how many cells will be failed in this distribution. In the end, we can come out with cumulative number. So once we have a cumulative number, we can also come out with a cumulative distribution. So for sure, this is just a first stage. And then by considering this distribution, whether is frequency and cumulative distribution, we can start to make the distribution plot as shown in the next slide. So basically, if we try to calculate, we try to plot this at the x-axis. So we consider this one in the y-axis, then we can come up with this very well-known distribution plot that whether the x-axis is considered each current, and then the y-axis is considered that how many fuses are failed in this current. So the results are best represented in the form as that's how we typically call as a histogram. As shown in this plot. So that's the very typical statistic analysis. If you have been already used Excel for a while, that's very easy to generate this histogram plot in the Excel. Of course, what we need is not only a pure histogram, but actually we are more interested in plotting this data in another form. Especially, we have already mentioned there is a cumulative distribution here. So it is common to plot the failure data in another way, which is cumulative distribution. So this is generally plotting as the number of values that occur at less than or equal to a given value is noted. It's not if you look at the text, for sure it's not easy to be understood, but that's just explained step by step here. So now we have the 2% here. We have a 2% until 100%. So basically, we just plot this cumulative number into the y-axis, and also we plot this upper current in the x-axis. So now if you look at this plot, so you will realize, for example, the point for 50%, this is a cumulative for the 50%. So that means we test up to this current is already 50% of the fuses are failed. And what will be the current for this condition? This is 9.8 amp. So that's in the case around here. So basically, we start to make the plot based on the data here, and then finally we can convert to another form. We are able to estimate the community distribution versus the different stress current. So by using this plot, we can also understand if we test up to this value, then 100% of fuses are failed. So in the end, this plot is become very useful because, as I say, now we are trying to produce thousands, 10,000s of product to our customer. So the customer is actually interested in which condition that will in the end lead into how many percentage of the value. So actually what they really want to know is the cumulative value data here. And we have a very specific name for this data, this distribution that we generally call as a cumulative distribution function. And we just very often just call the name. It's called the CDF. So the YX is actually as a CDF, which is a cumulative distribution function. By consider the cumulative distribution function, also can give a sense about the product uniformity. So, for example, if we compare the CDF in the two ways, the first one is just like the example here. So we have the testing currents between 9, 10, 11. So the first distribution can be, we start to see the value once the current is beyond 9 amp. Then reach to 11 amp, then 100% of our device are failed. So that's one case. Another case is we test, there's no any value until reach to 10 amp. All the devices are failed at 10 amp. So, which is better? Of course, we hope to have this case, because this case is kind of like ideal case. That means our product shows the very great performance, uniformity, that all of the product are only fail exactly at the 10 amp. That's a dream we wish to have, because that proves our product has a great uniformity. On the other hand, if we have the curve like this one, that means our product has a very poor uniformity, because you have very spread of your failure current. You have the failure current at 9 amp, you have a failure current at 11 amp. So this is not something we want to have. So this also suggests the wide distribution of this failure current also suggests this is a poor uniformity. So in the end, if you're trying to look at some of the industry, no matter from the literature or their product data sheet, you will very often to see they always will show the CDF versus a certain criteria to prove the uniformity of their data of their product is good. So of course the ideal case is this ideal case suggests that we have the very good uniformity. So with analyzing of this CDF, that gives us another further understanding of the uniformity for our product. So that's an important implication for the CDF function. Now we will start to look at a little bit details for the normal distribution function. The first one we want to define is, since we talk about the CDF, and there's also another important function, what we call the probability density function. Generally, we just call as PDF. So the probability density function defines the normal distribution function is fx has a familiar mathematical form as shown in here. So in this is a general form for the probability density function. And in this equation, whether the quantity of the sigma and mu are defined inside this equation. This normal distribution function actually is very well known, so I bet you guys already have seen these functions. So this is a function where looks like the bell shape. With a center as a mu, and with a standard deviation of the sigma. So this was mu minus, mu plus, mu minus, mu plus. So this is typically what we call the bell-shaped curve. So it's usually we call this z is equal to x minus mu over sigma. So that can simplify this equation from here to here. So in anyhow, just another simplified form for this normal distribution function. So far, this is just a reminder what you have learned already before. That's I think everyone should already knew about the normal distribution function before. Of course, related to the CDF, probably you are the first time to also understand the meaning of the CDF plot. Right now, we will start to bring you another concept that we call the statistical process control. That we call the SPC, and this is also considered the concept we call as a Six Sigma. So, the state-of-the-art IC fabrication process has approximately more than 50 masks and more than 600 individual process. So this is a average mask set versus the different generation technology here. So as the data show me here, below the technology, below the 10 nanometers, already we have the mask set more than 50, even beyond 70 max set here. And of course, this is because our process become complicated. Our device looks very complicated. We need a lot of masks to proceed our process. But the problem is each process state and masking level for sure can introduce defect as well, and all of which can potentially impact the yield and reliability. That we have already discussed in last week. As long as we have a defect, that always has a certain impact on the yield and reliability. And also, defect at any process state will impact the yield and reliability as well. So the question is how to handle the control process defect introduced by processing. So now we have to introduce a concept called statistical process control. So first, we back to our equation where we have already discussed is a PDF. So PDF, this is a probability density function, defines the form of a normal distribution is fx. It's shown me here. So this equation is widely employed in the industry to monitor the extent of process production quality control. So this equation is important for the quality control during the process. And especially we are interested in using a value called the sigma. Sigma is a measure of the spread of a major process variability. For example, sigma can be a measure for all kinds of the variable you are interested in. For example, in this case, it's a threshold voltage here. So in general, by consider the sigma, so we can define the certain information coming from this normal distribution function. So, for example, So the threshold voltage has a limit. So beyond this limit, a chip or entire wafer is considered as a zero yield. So for example, in our production, we can define the threshold voltage here, and we all know the threshold voltage has this normal distribution characteristic. And then which, for example, we define this is a boundary for 0.10% shift, and this is 1.1 10% increase shift. So beyond this range, we consider that the yield is equal to 0. So that's how this meaning for this text. So first, we will employ this normal distribution function, and then we can define a boundary. And once beyond this boundary, we consider as a yield is equal to 0. And also, with some basic information in the normal distribution function, we all know with 1 sigma, this is a center value, and this is a minus 1 sigma plus 1 sigma. So we all know with a range of 1 sigma, this already cover for 68.25% of all your amount. Consider all of your amount. So that's a plus minus sigma, 1 sigma, that's include for 68%. And with considering 2 sigma, that's we have the almost 95% compared to all of your product here. So there's a acceptable range for the critical parameters such as the threshold voltage, oxide charge, oxide thickness. So we can define there's a threshold for each parameter we are interested in, and then we define the certain spec here. In the end, we hope our spec, these values should be inside the value, what we call the upper control limit. So we have the UCL and LCL, and the UCL is what we call the upper control limit. That's a UCL. And we have a lower control limit. That's what we call LCL. And the reason we call the 6 sigma is because, as we already say, for normal distribution function, around 68% is between plus and minus 1 sigma. Around 95% is in between plus 2 and minus 2 sigma. And around 99.7% is between plus 3 and minus 3 sigma. So that's why we call this as a 6 sigma control. So in the end, we hope our data or performance or the spread of our parameters should be inside this 6 sigma here. So now, if the spread from positive 3 sigma to minus 3 sigma is small compared to the spread between UCL and LCL, so now we have the high certainty that the parameters well controlled for the production. So what does this mean? This means we consider this distribution function. So now if this is mu minus sigma, mu positive sigma, if this 6 sigma range is lying in between LCL and UCL, so now we have a very high confidence that our fabricate device, our fabricate product, the performance of our product are in between this UCL and LCL. So that means we have the very well parameter control. So now you can see this is example. This is a certain parameter deviation as a data shown here. This is the experimental date. So you can find out that the UCL is here and LCL is here. So our goal is try to make sure the production product that fabricate with the time always lying inside this UCL and LCL. So that's generally we call as a statistical process control. And of course, based on this information, if now we have the results, our LCL is here, our UCL is here, but unfortunately our process control is not that good. So in the end we have this distribution function. So this 6 sigma is larger than our UCL and then LCL. So that's it's an indication that we have the poor control for the product with a different fabrication time. So that's the purpose. We need to have this concept as a statistic process control with considering the 6 sigma. So in summary, we will make the distribution function, try to analyze our parameter, and then we want to make sure the 6 sigma of a certain parameter should be in line in the range between the UCL and then LCL. And of course, we have some more details related to the statistics process control. So the information you have to know is a more sophisticated method measure term for CP and CPK is determine the capability of a process. So the CP here is meant as a short-term capability. And the CPK here is called as a long-term process capability. So there's a mathematics considering these two terms, where CP is equal to UCL minus LCL over 6 sigma, and CPK is equal to CP times 1 over K here. So the K is a ratio of the mean drift to this UCL minus LCL over 2. So that's the definition for the K value here. So this is some of the detailed illustration with regarding for the CP here. So the capability index for CP, so CP equals 1 will become like here. CP larger than 1, that will become like here. So once we have this very narrow distribution, so that's good for the product quality control. So this is a narrow distribution. And there's some of the information. The value of CP and CPK of 1 are marginal, whereas 2 or 3 are much better because less of process window is covered by spread of a parameter. So here is some more information related to CP and CPK. And one of the difference between the CP and CPK is we can consider the plot. So the CP is a short term. So the short term for each, for example, short term for each step. So that's the distribution for each process step that can also cause a certain distribution of our parameter. So you can probably have the distribution for each step here. So that's a short term. There's illustration for short term. But the long term, it means you consider as an overall distribution after all of the process. So that will become like here. So it's basically as a merge for the short term to the long term here. And this come out with a question related to the accuracy and the precision. So with respect to the measurement, the most often asked question is that how accurate are they? And what precisions are they made? So here is a for example, just trying to give the concept related to the accuracy and also the precision. For example, the first one is the case we consider as a good precision and also good accuracy. The reason why we have the good precision is because we have the smaller sigma, but also good accuracy is because the small between the x1 minus x0. So that gives us an indication of the accuracy. Accuracy here. So that's the first case. And second, it's a case where we have the poor precision but a good accuracy. So why this case has a poor precision is because due to the larger sigma. But we still have the, in general, if you look at the center for this distribution, between the target inside the center is still small. So we still have the small x1 minus x0. And the third case is good precision, poor accuracy. So good precision is because of the smaller sigma here. But unfortunately, all the black dots are far away from the target. So that's a larger x1 minus x0. And the last one for sure is the worst one. We have the poor precision and poor accuracy. This is because we both have the large sigma and also the large x1 minus x0. Okay, so that's also some of the additional concept that's interesting to know. So finally, we move to another mathematics we should know. It's about the failure rate. So the failure rate is also equal to the degradation rate. In anyhow, just the equation that allow us to estimate the device degradation. So as we already know, reliability implies the time-dependent failure. So therefore, we must include the time factor into our CDF function. So we already talked about CDF, which is a cumulative distribution function. But also we know the reliability is a time-dependent process. So we must include the T inside the CDF. So this comes out with the capital F is what we usually consider as a CDF. It's equal to integration of Fy dy and from the minus infinity to the T. So that's because right now we have to include the time, so we have to calculate the time, integrate the time inside the CDF. So where the lower time limit is taken to be minus infinite instead of 0, because that's just for the mathematical purpose. And that gives us some simplified calculation. And for given population, capital FT is a fraction that fails up to time t, and it's related to the PDF. So PDF is a probability density function. So there's a certain correlation between the CDF and PDF where the FT is the capital FT over dt. So this is a probability density function. So basically we can also do the derivative again to calculate the FT. This is a small FT for PDF. So reliability, or sometimes we call as a survival function, can then be defined to indicate the surviving fraction, which is, so reliability means that the device can survive. So basically what we can do is we just 1 minus the value. So CDF is a value for all the devices have reached the value state. So if we consider 1 minus value, that's equal to the survival. So that means the reliability function. So in anyhow, for sure, I believe that in this classroom, I think most of you are first time, unless you already have certain working experience. So that probably you already heard about this community, because in the real fact, in the real product quality, we need this data. But if you are the first time, you probably will feel a little bit confused about all this calculation. But my point is that in the end, the equations are very simple. Probably the calculation sometimes looks be like the complicated, but in the end, we always try to simplify to a form that we can easily to use. So the failure rate, sometimes we call the failure rate, or we also call as a hazard rate, lambda t. Is defined as a number product that fail between t plus t and t between t and t plus delta t per time, which considering the incremental delta t, and as a fraction loss that survive to time t. So this statement is pretty confused. So just look at the equation. So the hazard rate lambda t is equal to the this equation, t plus delta t minus ft. So that's a value. And also the definition here is consider the delta t, because we consider the value, the CDF value in between this small delta t, but also we have to divide by 1 minus ft. The reason we divide by 1 minus ft is because we have to divide this reliability function. So in the end, this is become the small ft. Why it's become small ft? Because this one is exactly equal to this, right? As long as your delta t is approach to the infinite small, so that's equal to d ft over dt. So then we back to the function as a simple fine as a here. So this is 1 over 1 minus ft is equal to this one. So in the end, this equal to ft over rt. This one should be so in the end, if you try to calculate the failure rate or hazard rate will be just equal to the PDF over the reliability function. So now we will step by step to show that why we care about the failure rate, because in the end, if we try to put all the distribution function inside, you are surprising to know why in all of the mathematics, we prefer to use the exponential function. I think exponential function is a very powerful equation that has been used in all kinds of the science and engineer, no matter you are in the semiconductor field, in the physics field, in the chemistry field. In the end, it's always come out the first equation in addition to the linear fitting, the first equation come to our mind to do the fitting, we always come out with use the exponential, because in the end, the exponential, if we do certain calculation, that's give us some of the interesting results. That's why we consider exponential as a first guess. So in the reliability modeling or analysis, also the same, the exponential is one of our important equation, especially related to the exponential distribution function. So if we consider the exponential distribution function, the PDF for this exponential distribution function is written as ft is equal to lambda 0 exponential minus. So basically nothing special for this function. This is a very general exponential decay function, where lambda 0 is a constant. But of course, the problem we have for this equation is t, the time is not like the proper related to quantity, but it's the things we are interested in. So now we do what we have been already discussed. The CDF is basically as a minus infinite toward to reach to up to the t, and then lambda 0 exponential minus lambda 0. For example, here we use the dr here. So by doing this simple calculation to do the integration of this function, we come up with our CDF will be equal to 1 minus exponential minus lambda 0 t here. So now we have a PDF, we have CDF, and based on our logic, the next things we are interested in is the failure rate. So we just put the equation for failure rate where we have already derived before, which is equal to the PDF over 1 minus CDF. And you just try to put all the equation inside. The conclusion is very simple. So we have the small ft, which is equal to lambda 0 exponential minus lambda 0 t over this one, 1 minus exponential minus lambda 0 t. And then result is just equal to lambda 0. So the conclusion is that why the exponential distribution function is so attractive for us? Because in the end, the failure rate is a constant. So that means if in the future you consider the failure rate of your product, which will be failure with the time as a constant value, actually you can start to employ this exponential distribution function. So that's why, in addition to the linear function, always exponential is our first guess. And the reason why the exponential distribution function is important for the reliability modeling is because in the end, what exponential distribution function implies is that the failure rate for this product is considered as it's become a constant, because due to the constant failure rate, so we can use the exponential distribution function to do the reliability modeling and then analysis. So this is also another evidence, just echo what I have said. The equation sometimes looks very complicated, but as being an engineer, we always try our best way to simplify the result to the result that's easily to be remembered with a certain physical sense. So the calculation, if you go back to the previous several pages, I agree the calculation is sometimes very confused because we employ the distribution function, we need to do the integration, we need to do the certain new concept definition, for example, the failure rate. But in the end, if you look at the result and conclusion here, I think it's very straightforward. Okay, so we will take a short break and we'll come back after 10 minutes later. And by the way, please also to bring your homework in the front. No, it's just this category by itself. We can also consider like you can find one group.
Will it affect the data?
Yeah.
Oh, yeah, how steep?
But I think in general, the trend will be still roughly. It's always you keep the list of the number and the value. You keep the same, it doesn't matter. But it's important if you want to do comparison. Some kind of
It's just standard deviations calculations where we use probability and the calculator.
Yes.
Because we're not very used to the term sigma because we keep using standard deviations.
It's very similar to the concept of standard deviation.
Right. Yeah. So because it's a concept, we know that sigma is standard deviation, but it's also very confusing for us because we outside we only learn in terms of standard deviation.
Okay. Yeah, that's also because the last can be used for many different occasions. Yeah.
So this will be just the difference between the mean plus 3 standard deviation.
No. Actually, it's the first rule of define UCL and LCL. Our purpose is we need to make sure the Six Sigma will in between these two boundaries. If we can control in between these boundaries, that means it's very successful. So that could be, for example, this is 10% shift. Our product is 100 of our device, but all of them 6 Sigma in between these 10%. That means it's a very good product.
Okay. So that means it's just ensuring that everything that falls below this range will be a good standard that we have to maintain.
Yeah.
So that in terms of reliability, we can ensure that it's reliable.
This this here is mainly related to quality. So quality control.
Not model, it should be reliability.
Sometimes reliability is a time, but quality means that your product today and your product tomorrow should be with a very similar characteristic. 对。H
跟这个表现，我不知道。
没有关系。
但为什么要给那个？
对，这个是有关系的。对，以这个来说的话是会需要。
所以你需要知道说，就是这个只是部分。
等一下下课好，我能秀给你看一下。对，你要下课来找我。
老师，我想问 Sigma 的 Sigma 跟就是它的那个函数跟一般的 normal distribution 函数是一样的函数吗？
你是说什么意思？
因为像 Six Sigma 就是它下面有6个标准差。对。那它的函数就是用 normal distribution 函数去表示的。我觉得是啊，就是应该一样东西，对。只是它有分到6个。对，它只是它6的问题是说6个可以 cover 97%，对，所以你要 make sure 97%的你的所有的 distribution 都要在你的这个预期的这个 boundary spec 里。那就是如果假如说用在工业里面，对，就是它可以控制的范围，对，它可以制成控制范围，对 ，OK。对，所以我一直以为它可能会是不同的。我觉得应该是一样的，因为前面就是在讲，我们这边在讲就是这个就是 normal distribution。对，因为我之前在做研究的时候有用过这个。对，因为我刚好就是有用到统计的东西，所以因为我那个时候有画了一个叫做 quantile 的 plot，就是它也是很像。很像分布图，它也是用分布去看的，它是用分布转换的，所以它就会变成一个直线这样，这样，所以它应该是一样的，就是一样的东西。好，老师还有一件事情就是那个什么汉雷的那个，我们这个可能比较是这个，因为这边现在是有录音。对，我先讲吧。我们下一班，这一班有没有什么？下一班我给你讲。下一班我给你，就问你可以分配到哪个部分，然后先跟大家一起学习。
这里当中比较大，
越多时候还。 哦，真的？为什么现在公费了？
现在大概应该是13000，然后因为今天要把那个 iMac 的4片进去，所以再付8000。
OK， 那这样子的话，那这样子，换我先给你好，然后我先等那个评委才把那个他的钱交。对，OK，那所以现在你现在是因为先缴完那个 iMac 的税只剩下2000多，
应该是13000，所以应该是5000。
然后我现在要缴那个清大的，
交大的
是多少钱？
交大好像13000。
13000，这么贵。好，那我跟另外一个讲一下。
还是那交大的其实还没那么急。
它上面 deadline 上去。
那好像只是缴费通知单，缴费通知单就是要缴费。
它那个是用充费单点，它不是直接汇款。
它是这样。
对，
就是16000。
对，16000，它有 deadline。但这个通常也不能拖太久，因为拖太久会被锁卡。那这个通常是我们在店嘛？
对。
这个时候现金带电，我再拿给你。
帮我回去再确认一下。
OK， 然后再跟我讲，然后那我跟那个伟成讲一下，对，请他先赶快把那个，因为他之前真的奖学金拿到了，对。 Okay. Okay, so we have already shown the equation for PDF, CDF, and also for the hazard function. So now we will going to plot all three functions we have already described. So the first one is PDF. So the PDF equation is T is equal to lambda 0 exponential minus lambda 0 t. So based on the form of this equation, the equation should be look like as an exponential decay, where this is 1 over lambda 0, 2 over lambda 0, and 3 over lambda 0 here. And also, on the other hand, we can also plot the CDF. So CDF is equal to capital FT is equal to 1 minus exponential minus lambda 0 t. So basically it's a 1 minus of our PDF, it's a kind of similar to 1 minus of the exponential decay. So in the end, this graph will be similar to here, where this is 1 over lambda 0, 2 over lambda 0, and 3 over lambda 0 here. And also the last one is a hazard function. Which we have already shown in the case of a exponential distribution function, the lambda t is equal to lambda 0. So that means this is equal to 1 over lambda 0, 2 over lambda 0, and 3 over. So this is a constant, as shown here. So due to ease in dealing with a constant failure rate, the exponential distribution function has proven popular as a traditional basic for reliability modeling. So the constant failure rate modeling have been already used for a very long time. It's also one of the popular, although the concept is just a constant, probably sounds like easy, but it has been already widely used in the many applications. And this is given as a one example that even though this is a constant value, but that's already powerful for us to do the value rate modeling. So these examples come from the military handbook. So the military handbook is just, the meanings come from the name. It's a semiconductor device that being used for the military application. Of course, if you need to use for the certain application, for example, for military in this case, they also need to specify the value rate for their component use. So that's in the military handbook already described, they use a constant value rate. This is for sure, this is in the USA military. And so this is in the case, you can see, this is for the military handbook for the transistor low frequency silicon FET. And this is description for the N channel and P channel frequency silicon FET with the operation frequency up to 400 megahertz. And in this military handbook, they already define the value rate can be calculated as this component. This is also shown here. So where lambda P is a part value rate and lambda B is a basic value rate, usually expressed by the model rate relating to the influence of electrical temperature stress on the part. And the individual P factor take into account the role of the temperature, quality, environmental as well. So let's just look at as one example, how do we calculate value rate in the specific condition. So for example, in the case of a plastic small signal MOSFET, so now we have to look at the related information here. The first one is a MOSFET. So the MOSFET gives us a lambda B, which is equal to, this is the best value rate lambda B here. And at a 30 Celsius degree, so let's look at the table where the 30 is here. Use a specific, this is a condition that we consider that this MOSFET is being used for the space flight. A value rate, so then we can start to estimate the value rate. So the value rate would be equal to this is value come from MOSFET 0.012 times temperature 1.1 and times all other details. For example, this is plastic, so here is quality factor. So this is a MOSFET based on the certain plastic. So that's also give the factor of the A. And also we have the certain, this number, if we try to calculate all, then we can come on with this one, with a 0.07 per 10 to 6 hours. That's equal to the 37. Usually we define this as a feet. So that's the very basic application for reliability modeling. So this value inside this military handbook, for sure they have already done a lot of analysis, and they have the huge database in the end to come up with the value rate for the MOSFET is 0.12, and the value rate for the JFET, which is another device, and the value rate for the temperature, the value rate for the different materials, and so on. And therefore, with all this information, they can start to estimate what will be the total value rate, consider all these specific conditions. In the end, it come out with the time with 0.07 0.037 per 10 to 6 hours. So that's what we call the fit here. So the fit is, the full name for the fit is value in time. So it's defined as a number of values can be expected in the 1 billion device hour operation. So that means if we have a 1 fit, so that means you will have a 1 device value if you operate for 10 to 9 hours. So that's already 10 to 9 hours is very long time. And then if we have 1 fit, that means we have this quantity that will be value, 1 value in the case of a 10 to 9 hours. So in this case, based on the definition, so 37 fits, that means if we operate the pulse over 10 to 9 hours, total will be estimated 37 device will be failed in the based on these numbers here. So this is just an example to showcase that what would be the information we can have based on the constant modeling with considering the different kind of the conditions. Of course, in this class, what we will teach is not only for the exponential distribution. We will have to learn some additional more, which is even more often used than the exponential. The next one we will teach is a log-normal distribution. So the shortcomings in the exponential distribution function has a certain limitation. Therefore, we have to propose some alternative distribution function to model reliability data. And one of the most popular of these these distribution functions that can be used for reliability modeling is a log-normal distribution. Log-normal distribution function, which the full functions can be shown in the slide where the PDF is shown me here. So in here we won't talk too much detail about how do we get this equation, and later on how do we derive the CDF, PDF, and other function. So basically, if you look at the answer for this equation, so you can understand this should be the calculation beyond the capability for the hand calculation. This needs a specific software to help us. But anyhow, the equation is not that important. It's more important is what will be this distribution imply for us. So this is the PDF for the log-normal distribution, and we realize that inside this equation, first, this equation related to mu, and is also related to the sigma. So the first is mu, which has a physical significance of representing the median time. Or time when 50% of the distribution will fail, which usually we call as a T50. So the mu is equal to natural log T50. 50. So T50, that means it's a time when 50% of the distribution will fail here. And secondly, there's a shape parameter of the sigma, which will strongly influence the shape of the small ft and then the capital FT here. So now if we try to plug this is PDF, so we try to plug the PDF in here. So now the different sigma, this is a different, the shape parameter will influence the shape of this PDF and also will influence the CDF as shown here. And the large values of sigma, when sigma is larger than 2, this reflects initial high value rate that decrease with the time. So you can see this is a hazard function. So this is sigma equal to 0.1. This is sigma equal to 0.15. And this is sigma equal to 1. And therefore, if the sigma is larger than 2, the curve is expected shown like this for the case of sigma equal to 2. So now you definitely will be interesting and sometimes confusing why the normal distribution is important. Because if you recall the beginning when we talk about the life for the human being or life of a semiconductor device, we have a very famous for the Best tube curve. So the Best tube curve is a curve look like in this way. We have the 3 phase for the one human or one product. So in general, we can divide by 3, which is 1, 2, 3. And the first one is a situation we call the infant mortality. And the second one is what we call the steady. And the third one is what we call the wear out. So this is something we have been already mentioned in the introduction to say about the Best tube curve. That's exactly similar to the case of the no matter for human being or for our semiconductor product. And the powerful for the log-normal distribution is we can use the log-normal distribution to model these 3 phases. So if you look at the hazard function, which is also equal to the value function. So the high value rate decreasing with the time in the phase 1, which is we call the infant mortality, which will be exactly equal to the situation as long as if we try to have a large sigma, right? So as already said, the shape parameter will highly influence on the FT, small ft and capital FT, and also highly influence on our value function, which is hazard function. So if we play a trick, try to put the sigma as larger as possible, basically we can use this part to model this region. And also the cool thing is that not only we are limited to model this region, we can also model this region as well. So where is the steady? Steady state is roughly equal to the constant which is here. So if you put the sigma roughly around 0.5, basically you can get the value pretty constant. That's exactly similar to the case of our static. And then finally is a wear out. So wear out, that means we start to see the degradation. We start to see the increase of value as the time pass by. And therefore, which sigma can be used to model this one? That will be equal to this one if the sigma is very small. So that's why the log normal distribution function is very popular, used to model the lifetime in the reliability analysis, because we can basically use the one function which just play the sigma value. We are able to model the whole life for one semiconductor product, from the beginning of the infant mortality to the second phase of steady to the last part for the wear out. So that's why we are pretty interested use the log normal distribution. So therefore, the log normal distribution can represent the early values. Steady state. And the wear out region in the life of a device. So the previous, we talked about exponential distribution, but unfortunately, exponential distribution is only considered as a constant value, so cannot be modeled all these three phases with a simple exponential distribution function. But now if we apply the log normal distribution function, we can use one equation to model all three phases. That's why this equation, this distribution function, are so attractive for us. And of course, the equation for log normal nowadays it's very not usually we won't use hand calculation for log normal because the equation in here looks very complicated. But in the past, some of the researchers have created this plot that give us a more easy way to consider to use the log normal distribution. So this is just one example. So the x-axis is a time over median lifetime, and y-axis is a failure rate, and all this plot is based on the log normal. So in the case of the t over t50 is equal to 3 times 10 to minus 3. So that would be roughly here. So in the end, we got the failure rate of the 10 phase is equal to 40 years. So this is a useful plot for us for the quick estimation. But the real important thing is we need to consider the log normal distribution modeling for the inside the CDF plot here. So this is a failure probability. In here is a community failure probability. So that's equal to the term we have already mentioned. That's a CDF. And the x-axis is a time. So basically, we can plot all these dots are the experimental data. And this straight line is modeling based on the log normal distribution. So we can see in this case, we can use a log normal distribution to model the failure data very well. So this is a log normal distribution of failure time for the gallium arsenide laser that testing at 70 Celsius degree. So that's one example. And also we have been already introduced inside the log normal distribution. There's a time factor very important. That's what we call the T50. So the T50 means that the time that reach to 50% of the device value. So that's what we call the T50. So now, if we assume this testing is done with a 1,000 testing device, so that means if you test this gallium arsenide laser up to 700 hours, right? So the x-axis around 700 hours, you already have 500 device fail. So this is the T50's meaning. The meaning is that when you test up to this time, you have the 50% of your device fail. But of course, if you consider the modeling or prediction, if you want to ship, you want to qualify, you want to test on your product, you are not only interested in the 50%, you are actually want to tell your customer, and how about which timing that will only give us a 1% value, because 1% can be certainly acceptable values, right? If you ship like 100 device and you tell that, okay, you can, how large amount of time you use and you can have a 1% value, because usually no customer will buy your product if you only provide the data for 50% value, because 50% is a huge amount of the device. So they will be only interested in the case of a 1%. So where is a 1%? Here is a 1%. So in this case, that means you test probably up to 70 hours. You use for 70 hours, that's already have the 1% value. So this is how this plot can tell us. So if you have the 70 hours operating or biasing, you have a 1% value. So that means you already have the 10 device fail. But of course, what the customer, your customer want is definitely will never satisfy for 1% value, because he sell for 1,000 products, still got the 10 products fail. That still will cause a huge problem. So in reality, in the industry, the real consideration, what they wish to have is a 0.01%. So, but now, what you can do to estimate the 0.01%, you have no data here. So that's why we need this modeling, because this modeling gives us a chance to do the prediction. So if we extend this plot to somewhere here, and let's say this point is a 0.01 percentage. Then we can start to estimate the time here. So this will be the T for 0.01 percentage value. And probably that will be equal to 10 hours. So finally, if you fabricate this device, but unfortunately, you can only tell your customer you can only operate for 10 hours operation, because the 10 hours operation already cost 0.01% values, which is equal to one device. One device fail, then that will depend on whether your customer will still buy it or not, will reach their requirement or not. So in the end, this is the way that how we use this distribution data to do the lifetime prediction. In the past, we did say that there's a constant, so we can also use a constant. But now we use another method to give us the value that's related to the percentage. So that's the most important part. So now, because the reason why we employ this statistic, because we know we want to understand the value percentage versus the time. Is a key. That's why we need to have the distribution function. Not only distribution function, we need to also integrate the distribution function with time and become the CDF, because in the end, we want to know the CDF versus the time. So that's a very general scope that everyone who are in the reliability field, why they always in the end have to employ the log normal distribution, or later on we will talk about the Weibull distribution. It's always based on the same motivation. So the next we are interested in is getting more and more important. It's about the Weibull distribution. There's a slightly different reason. Sometimes we use a log normal, sometimes we use a Weibull distribution. Later we will talk about this. We will bring you some example, and we will also talk about why the physics inside will lead into some case will be more preferred for Weibull, some case will be more preferred to log normal. But in here, just a general introduction for Weibull distribution. So Weibull distribution is a two-parameter distribution. Also, we can adjust him. There's a two parameter we can adjust. The first one is a time scale parameter. And the second is a shape parameter. So the time scale parameter is generally we call the alpha. The shape parameter is we call the beta. And then the general form for PDF is shown here. So the beta t, beta minus 1 exponential t over alpha beta alpha, beta, and beta, alpha are constant. And that's a PDF. And CDF is an integration, so which is equal to Ft is 1 minus exponential T over alpha beta. And the most important one is CDF, especially this one. And the rest of the concept to deal with this equation is the same, like the previous discussion with exponential, with log normal. Since we know the PDF, since we know the CDF, and next one we are interested in is a failure rate function, which is a Hazard function. So this is a PDF for Weibull distribution, and this is a CDF. And the one we are interested in is a Hazard function. So inside the Hazard function, this is the Hazard function here. And if beta is equal to 1, then this will back to the original distribution function. So if you beta is equal to 1, and then the equation will be simplified as a exponential function as well. And if beta is equal to 2, there's another name which we call the Rayleigh distribution. But the reason that why the Weibull distribution is very popular for reliability modeling, the reason is the same like one in log normal, because this distribution is powerful for the base tube curve, can represent the 3 phase for the base tube curve as well, where this is an infant mortality, and second is a steady, and last one is a wear out. So if we consider the case when beta is smaller than 1, like here, so basically we can use this to model the infant mortality. If the beta is equal to 1, that can be used for the steady. And also, if the beta is larger than 1, we can use for the wear off. So this is the Hazard function. So we will stop here, because the next few slides we will start to explain the difference between the Weibull and the normal, and when can we start to use, and what will be the physics related to this distribution. But I think today is enough equation and enough new thing for everyone. So we will stop here, and then we'll continue the rest in the next week.